What if the ancient myths were more than just stories? What if, in their poetic descriptions of sun gods and celestial origins, they captured an essential truth about our existence? Could it be that, in some fundamental way, the sun truly is our God, not as a supernatural entity, but as the very source of our being? On the most basic level, the sun's radiant energy sustains life on Earth. Its warmth maintains temperatures within the critical range that allows liquid water to exist, creating the conditions necessary for biological processes. Photosynthetic organisms capture sunlight and convert it into chemical energy, fueling the intricate web of life. Every breath we take, every movement we make, is ultimately powered by solar energy transformed through countless biological interactions. Without the sun, Earth would be an icy, lifeless world adrift in the void. Yet, our connection to the sun runs even deeper. We are not merely recipients of its energy, we are, quite literally, built from the remnants of its cosmic ancestors. Just as ancient myths speak of sun deities born from primordial forces, our sun itself is a descendant of earlier stars. It was not the first of its kind, but a member of a long lineage of celestial bodies that have continuously shaped the universe. The sun emerged from a stellar nursery, a dense cloud of gas and dust pulled together by gravity. As matter accumulated, it compressed and heated until nuclear fusion ignited in its core, giving birth to the luminous sphere we see today. But where did this vast nebula come from? The answer lies in the life cycles of stars that came before. Our sun is classified as a population 1 star, meaning it was formed from the enriched remnants of older, now long extinct stars. These ancestors, population 2 stars, transformed the primordial hydrogen and helium of the early universe into heavier elements through nuclear fusion. In their final cataclysmic deaths as supernovae, they scattered these elements across space, seeding the next generation of stars. But even these were not the first stellar architects. Theoretical models predict the existence of an even earlier generation, the elusive population 3 stars, the first to ignite after the Big Bang. These stars, composed purely of hydrogen and helium, were colossal and short-lived, burning with an intensity that rapidly fused lighter elements into the building blocks of future celestial bodies. Though never observed directly, their fingerprints remain in the chemistry of ancient stars and the cosmic background radiation. Thus, our sun is the product of an ongoing cosmic cycle, a vast and intricate process of creation, destruction, and rebirth that has unfolded over billions of years. The elements that make up our bodies, the carbon in our cells, the oxygen we breathe, the iron in our blood, were all forged in the hearts of stars long before our solar system even existed. Perhaps then the ancients were onto something. The sun is not just the center of our solar system, but a testament to the universe's grand design. It is the latest in an unbroken chain of cosmic fire, linking us to the very origins of matter itself. And so, in a way, the sun truly is our God, not in the form of myth, but as the ultimate source of life, energy, and existence itself. The alchemist's dream, from ancient transmutation to modern nuclear science. The year was 1782. In the hallowed halls of Great Britain's Royal Society, a claim emerged, one so audacious that, if true, it would resolve one of humanity's most enduring mysteries. A young and ambitious chemist, James Price, asserted that he had unlocked the secrets of transmutation, the fabled transformation of base metals into gold. Unlike the common charlatans who thrived on deception, Price presented empirical evidence, bolstered by experiments conducted before witnesses. His method, he claimed, involved the use of 2 mystical powders, a white powder that could turn mercury into silver and a red powder that could convert it into gold, producing an astonishing 60-fold increase in mass. While many of his contemporaries remained skeptical, his achievements did not go unnoticed. The University of Oxford conferred upon him an honorary medical degree, not explicitly for his experiments, yet the timing suggested a connection. To the public, it seemed that Price had finally proven alchemy to be a science rather than a fantasy. However, When the Royal Society pressed for a demonstration under its direct supervision, Price hesitated. He argued that the synthesis of these powders was so physically and financially exhausting that it rendered the entire process impractical. He insisted that his reputation as an honorable scientist should suffice to validate his findings. But in the face of mounting scrutiny, he relented. In January of 1783, Price stood before his esteemed peers, prepared to replicate his miracle. Yet, rather than performing alchemy, he consumed a vial of laurel water, rich in cyanide, and perished before their eyes. With his death, his secrets were lost, and his claim was cast into the realm of myth. Yet the desire to transmute elements did not die with James Price. It merely transformed. The dream of alchemy persisted, its spirit reborn in the crucible of modern physics. It was no longer gold that scientists sought, but a deeper understanding of matter itself. This quest would find its champion in a man who would revolutionize science, Ernest Rutherford. Born in 1871 in New Zealand, a remote British colony, Rutherford's brilliance propelled him from a single-room schoolhouse in Havelock to the hallowed halls of the University of Cambridge. At the turn of the 20th century, radioactivity was a nascent field, and Rutherford was among its earliest explorers. In his laboratory at McGill University in Canada, he and his colleague, Frederick Soddy, made a startling observation. Thorium, a heavy element, was spontaneously decaying into radium, a different element altogether. The implications were staggering. Soddy, in his excitement, proclaimed that they had discovered the secret of transmutation, the very goal of the ancient alchemists. But Rutherford, ever wary of the stigma attached to pseudoscience, cautioned him. For Mike's sake, Soddy, don't call it transmutation. They'll have our heads off as alchemists. Despite Rutherford's reluctance to embrace the language of the alchemists, their work marked a profound shift in scientific understanding. They had discovered that elements were not immutable. They could change, albeit not through magical powders, but through the hidden forces within the atom. By the 1920s, Rutherford had proven that elements could be intentionally altered. He demonstrated that by bombarding nitrogen atoms with alpha particles, energetic helium nuclei, he could produce hydrogen, an entirely different element. The experiment was further refined by Patrick Blackett, Rutherford's student, who used a cloud chamber to capture the moment of nuclear transformation. The photographic evidence left no doubt. Nitrogen had become oxygen. Blackett's work earned him the Nobel Prize in Physics in 1948, but the true revolution had already begun. Rutherford himself acknowledged the implications, remarking, "It is now possible by modern methods to produce exceedingly minute quantities of gold, but only by the transmutation of an even more costly element, platinum." Though his statement carried a touch of irony, it underscored a fundamental truth. Transmutation was real, but it was not economically viable. This newfound understanding of atomic structure would give rise to the most transformative scientific advancements of the 20th century. No longer were elements defined solely by their mass, as the ancients believed. Instead, the defining property of an element was its proton count, the number of positively charged particles in its nucleus. Change that number, and you change the element itself. Transmutation, therefore, could be achieved through several means. The first was through natural radioactive decay, in which an unstable nucleus emitted particles, thereby transforming into a lighter element. The second was through nuclear fission, in which a large atom, such as uranium, was split apart, a process harnessed for energy production and weaponry. The third was through nuclear fusion, the very process that powers the sun, wherein two smaller atomic nuclei merged to form a heavier element. Of these, fusion remained the most elusive and tantalizing goal. Nuclear fusion is the key to understanding the sun's extraordinary power. At its core, the sun fuses hydrogen atoms into helium, releasing an immense amount of energy in the process. This process is governed by two competing forces: the electrostatic repulsion between positively charged atomic nuclei and the strong nuclear force that binds them together. The strong force, though immensely powerful, operates only at extremely short distances. Overcoming the natural repulsion between atomic nuclei requires conditions so extreme that they are scarcely imaginable. Within the Sun, where gravity exerts an unrelenting inward pull, fusion occurs at a relatively modest temperature of 15 million degrees Celsius. But on Earth, absent the Sun's immense gravitational compression, scientists must generate temperatures exceeding 150 million degrees, 10 times hotter than the core of the Sun, to force nuclei close enough for fusion to take place. The allure of fusion lies in its promise. Unlike fission, which produces long-lived radioactive waste, fusion generates immense energy with minimal byproducts. Its fuel, hydrogen isotopes such as deuterium and tritium, is abundant, extracted from water and lithium. If harnessed successfully, fusion could provide a virtually limitless, clean energy source. Yet, despite a century of research, controlled nuclear fusion remains just beyond our grasp. The technical challenges are monumental. Plasma, the high-energy state of matter required for fusion, must be confined and stabilized within a reactor. The most promising approach, magnetic confinement, relies on powerful electromagnetic fields to trap plasma within a toroidal chamber, such as those found in tokamak reactors. Another method, inertial confinement, involves compressing tiny fuel pellets with intense laser beams to induce fusion. Both techniques have yielded progress, yet neither has achieved sustained, net positive energy output. Still, the pursuit continues. In laboratories across the world, scientists refine their methods, inching ever closer to the dream of practical fusion energy. Projects such as the International Thermonuclear Experimental Reactor in France and the National Ignition Facility in the United States stand as testaments to human ingenuity and perseverance. The journey from alchemy to nuclear science is one of the most remarkable sagas in human history. What began as a mystical quest for gold evolved into a profound exploration of the fundamental nature of matter. Today, transmutation is no longer the work of alchemists, but of nuclear physicists. We can transform elements not through arcane rituals, but through our mastery of atomic forces. The ultimate triumph, however, lies ahead. The quest to harness the power of the stars continues, driven by the same relentless curiosity that once inspired the alchemists. As we stand on the brink of a new energy revolution, we are reminded of an age-old question posed by the great physicist Arthur Eddington. What is the source of the heat which the sun and stars are continually squandering? Fusion, the cosmic fire and humanity's pursuit of the stars. In the early 20th century, at the annual meeting of the British Association for the Advancement of Science in Cardiff, the English astronomer and physicist Arthur Eddington posed a deceptively simple yet profound question to his colleagues. What powers the sun? At the time, the prevailing wisdom among scientists attributed the sun's radiance to gravitational contraction, a theory holding that as the sun's immense gaseous mass collapsed under its own gravity, the compression generated heat, much as the young Earth had done when it first coalesced from cosmic debris. While this theory explained the immediate source of solar heat, it bore an inherent contradiction. By the early 20th century, geologists and physicists had established that the Earth, and by extension the solar system, was billions of years old. However, calculations showed that if the sun's energy derived solely from gravitational collapse, it would have burned out in a mere 20 million years. The theory, Eddington contended, was not merely outdated. It was a corpse that had yet to be buried. Seeking a new answer, Eddington turned to the emerging field of nuclear physics, pioneered by his contemporary, Ernest Rutherford. He theorized that the sun must be tapping into an unknown and vast reservoir of energy, an energy source that could only be subatomic in nature. He proposed that deep within the sun, hydrogen atoms were fusing into helium, releasing an extraordinary amount of energy in the process. More than just explaining stellar luminosity, Eddington's insight laid the foundation for modern astrophysics, revealing that stars were not merely celestial lamps, but cosmic forges responsible for creating the elements that constitute our universe. Eddington estimated that this nuclear process could sustain the sun for 15 billion years, a figure slightly high by modern standards, but conceptually correct. His work did not just provide an answer to the riddle of stellar power. It ignited a new question: could humanity harness the power of the stars? Over the past century, scientists have pursued that question with fervor, recognizing that nuclear fusion represents a potential key to an abundant, clean, and near-limitless energy source. Yet, as history has often shown, the mastery of such forces holds both the potential for prosperity and the peril of destruction. The lesson of the brown dwarfs: an alternative path to fusion. While our sun and other true stars achieve fusion through the intense pressures of their immense gravitational fields, they are not the only objects in the cosmos capable of nuclear reactions. Brown dwarfs, celestial bodies that exist in the liminal space between massive gas giants and the smallest stars, offer a compelling lesson in alternative fusion pathways. Too small to sustain the fusion of ordinary hydrogen, brown dwarfs instead undergo a different kind of nuclear reaction, one that relies on an isotope of hydrogen known as deuterium. Unlike protium, which consists of a single proton, deuterium possesses an additional neutron bound to the proton by the strong nuclear force. This extra neutron reduces the energy barrier required for fusion, allowing brown dwarfs to generate heat despite their lower mass. Deuterium is relatively abundant in Earth's oceans, where 1 in every 5,000 hydrogen atoms is a deuterium isotope. In contrast, in Jupiter's atmosphere, this ratio drops to 1 in 40,000, a figure closer to the natural cosmic abundance of deuterium. This property of deuterium, that it requires less energy to fuse than protium, has drawn the attention of scientists seeking to recreate stellar processes on Earth. If nuclear fusion is to become a viable energy source, humanity must find a way to exploit this unique isotope's potential. The National Ignition Facility, humanity's first glimpse at controlled fusion. One of the most ambitious attempts to achieve nuclear fusion on Earth has come from the National Ignition Facility in California. Here, scientists employ a novel technique to recreate the conditions necessary for fusion by targeting a tiny fuel capsule with an array of 192 ultraviolet lasers. The capsule, composed of synthetic diamond and cooled to temperatures just above absolute zero, is placed inside a golden cylinder no larger than a pencil eraser. In an instant, the lasers deliver an immense pulse of energy, causing the capsule to implode. This implosion generates the extreme temperatures and pressures necessary to trigger fusion, mimicking the energy dynamics found in brown dwarfs. At the heart of NIF's experiments lies the fusion of deuterium with tritium, a third isotope of hydrogen that contains 2 neutrons in its nucleus. When deuterium and tritium combine, they yield helium-4, the most abundant isotope of helium, and release an unbound neutron carrying 80% of the reaction's energy. In August 2021, NEF achieved a historic milestone. A single experiment fused approximately 200 micrograms of deuterium and tritium, momentarily generating a staggering 10 quadrillion watts of power, nearly 700 times the output of the entire United States electrical grid. However, this burst of energy lasted only 100 trillionths of a second and produced a net output sufficient to power a light bulb for just 6 hours. More importantly, the reaction reached 70% energy efficiency, edging ever closer to the long-sought goal of break-even, where energy output surpasses energy input. Despite this progress, 2 fundamental challenges remain. First, fusion reactions must generate more usable energy than they consume. Second, they must be sustained long enough to be practical for power generation. While NIF's method has shown promise, scientists continue to search for alternative approaches that can yield self-sustaining fusion reactions. The most ambitious project in the quest for nuclear fusion is the International Thermonuclear Experimental Reactor in France. Slated for activation in late 2025, ITER aims to be the first facility to produce net positive energy through fusion. The team behind ITER hopes to generate 10 times the energy input, demonstrating that fusion can be a viable power source. However, even if successful, ITER's energy output will not be captured for use. it will serve purely as an experimental proof of concept. Beyond deuterium-tritium fusion, alternative fuels such as helium, 3 hold promise for a cleaner fusion process, producing fewer radioactive byproducts. Some scientists speculate that the Moon, after billions of years of exposure to the solar wind, may harbor significant quantities of helium-3. If so, future lunar missions may be tasked not just with exploration but with resource extraction, potentially igniting a new space race for fusion fuel. Long before the first stars, supernovae, or brown dwarfs began forging elements in their nuclear furnaces, there was a time when the universe itself was a fusion reactor. In the seconds after the Big Bang, as matter and energy condensed from the primordial chaos, nuclear fusion occurred on a cosmic scale. Hydrogen nuclei combined to form helium, and trace amounts of lithium and other light elements emerged. This brief but profound epoch, cosmic nucleosynthesis, set the stage for everything that followed, shaping the chemical makeup of the universe and enabling the eventual formation of stars, planets, and life. The pursuit of nuclear fusion represents humanity's attempt to reach back into this ancient, fundamental process and harness it for the future. As scientists continue their efforts to ignite a sustained fusion reaction, they are not merely seeking a new energy source. They are attempting to command the same cosmic fire that has shaped the universe itself. Whether this fire will illuminate a brighter future or serve as a force of destruction remains, as always, in humanity's hands. Big Bang nucleosynthesis, the cosmic alchemy that forged the first elements. If one were the 5th century BCE philosopher Empedocles, they might choose to hurl themselves into a volcano in an attempt to convince their followers of divine status. While this tale is likely myth, Empedocles is better remembered for a more enduring intellectual contribution, his efforts to define the fundamental nature of the universe. In his poem Periphysios, Empedocles introduced the idea that all substances in nature arise from a combination of 4 fundamental roots, a concept later adopted by Plato, who renamed them stoicheia, giving us the term elements. Though these ancient conceptions have long been superseded, they reflect a profound and enduring human desire to uncover the fundamental building blocks of existence. Today, we recognize 118 chemical elements, most of which are arranged within the periodic table in accordance with their shared properties. The heaviest of these elements, however, do not occur naturally in any significant abundance, as they decay too rapidly to persist. The elements that do comprise the observable universe have their origins in the tumultuous life cycles of stars. Through nuclear fusion in stellar cores, stars forge elements up to iron, but elements heavier than iron require more extreme processes, such as the cataclysmic death of a star in a supernova, or the gradual neutron capture within certain types of long-lived stars. Even more violent still is the collision of neutron stars, an event first directly observed in 2017 through gravitational waves detected by LIGO. When 2 neutron stars spiral into one another and merge, the resulting explosion, known as a kilonova, can synthesize and disperse an array of heavy elements. One such event provided direct spectroscopic evidence of strontium, atomic number 38, demonstrating that these cosmic cataclysms contribute to the elemental diversity of the universe. Yet before the first stars were born to forge heavier elements, before supernovae enriched the cosmos with their metallic remnants, there was an even earlier moment of elemental creation, one that unfolded within the first few minutes, after the Big Bang itself. The most energetic moment in the history of the universe was its very inception, the Big Bang. In its immediate aftermath, the universe was an incomprehensibly hot and dense sea of fundamental particles, a primordial plasma governed by extreme temperatures and rapid expansion. Within the first microsecond, temperatures were still around 10 trillion degrees Celsius, conditions so intense that individual quarks, the fundamental constituents of protons and neutrons, could not yet bind together. But as the universe expanded, it cooled, eventually allowing quarks to coalesce into hadrons, forming protons and neutrons, the building blocks of atomic nuclei. Of the 6 known types of quarks, 2 dominate the everyday matter of our universe: the up quark and the down quark. The delicate balance of these quarks determines whether a hadron will become a proton or a neutron. Since hydrogen is defined by the presence of a single proton in its nucleus, the moment that protons emerged from the early quark soup was, in effect, the birth of hydrogen, the universe's first element. While neutrons were also initially present in equal abundance to protons, their slightly greater mass made them more susceptible to decay. Within a matter of minutes, neutrons were transforming into protons, electrons, and antineutrinos via beta decay. By the time the universe had cooled sufficiently for nuclear fusion to occur, the neutron-to-proton ratio had dropped to roughly 1:7, an imbalance that would go on to shape the elemental composition of the cosmos. The first step in nucleosynthesis, the process by which atomic nuclei form, was the creation of deuterium, an isotope of hydrogen consisting of one proton and one neutron. Though deuterium could, in theory, have formed immediately, the extreme temperatures of the early universe made its existence tenuous. High-energy photons were so abundant that any newly formed deuterium nuclei were quickly blasted apart. This phase, known as the deuterium bottleneck, temporarily stalled the formation of heavier elements. However, as the universe continued to expand, its temperature gradually fell. Around 300 seconds after the Big Bang, conditions had cooled sufficiently for deuterium to survive intact. At last, the bottleneck broke, and the universe could proceed with further nuclear fusion. Deuterium nuclei combined with protons and neutrons to form helium-3 and subsequently helium-4, the most stable and abundant isotope of helium. This process of Big Bang nucleosynthesis, first theorized in 1948 by Ralph Alpher and his mentor George Gamow, provided a theoretical foundation for understanding the universe's earliest chemistry. In their now famous Alpha Beta Gamma paper, Alpher described how the extreme conditions of the early universe could drive nuclear reactions, transforming hydrogen into helium and setting the stage for all subsequent stellar nucleosynthesis. Yet, while the process of fusion within stars can create a vast array of elements, the primordial Big Bang nucleosynthesis was constrained by a time-sensitive limitation. The universe was expanding and cooling too rapidly to allow the formation of elements heavier than lithium in any significant quantity. By the time the universe was mere minutes old, the temperatures required for fusion had already faded, leaving behind a cosmos primarily composed of hydrogen and helium, with trace amounts of lithium and beryllium. Though the universe was born with only a handful of elements, these primordial constituents laid the groundwork for everything that followed. The hydrogen and helium synthesized in the Big Bang would later coalesce under gravity to form the first stars, igniting nuclear fusion within their cores. These first-generation stars, known as population 3 stars, would burn brightly and die spectacularly, forging heavier elements in their fiery deaths and seeding the cosmos with the raw materials needed for planets, moons, and ultimately, life itself. From the violent chaos of the Big Bang to the intricate nuclear alchemy of stars and supernovae, the history of the universe is written in the language of element formation. The very atoms that make up our bodies, the carbon in our cells, the oxygen we breathe, the iron in our blood, owe their existence to a chain of cosmic events set into motion nearly 14 billion years ago. And while the details of nucleosynthesis continue to be refined through astrophysical observations and theoretical advancements, one thing remains clear. The universe is, and always has been, an extraordinary factory of creation, assembling the fundamental ingredients of existence from the most extreme and beautiful forces nature has to offer. The cosmic forge, the end of Big Bang nucleosynthesis, and the seeds of a heavier universe. While hydrogen can exist without neutrons, helium cannot. The mutual repulsion of its two positively charged protons would make an isolated helium-2 nucleus an impossibility, as the electromagnetic force would overwhelm the nascent structure before it could even take hold. However, with the presence of just one neutron, the strong nuclear force, the fundamental glue of atomic nuclei, becomes sufficient to overpower this repulsion. The result is helium-3, a stable isotope formed in both the early universe and through modern cosmic processes, such as interactions with high-energy cosmic rays. Left undisturbed, helium-3 is effectively eternal, persisting until the end of time itself. Yet, the most abundant form of helium is not helium-3, but helium-4, an isotope composed of 2 protons and 2 neutrons. Its formation in the primordial universe was dictated by the same forces that govern the fate of all nucleosynthesis. The fusion of deuterium with either helium-3 or tritium provided the primary pathway for helium for synthesis, giving rise to the most stable composite nucleus known to physics. In nuclear physics, helium-4 is described as doubly magic, possessing a symmetrical arrangement of protons and neutrons that makes it exceptionally resistant to decay. This unparalleled stability made helium for the favored outcome of early nucleosynthesis. The universe, much like a great celestial alchemist, displayed a remarkable preference for its creation. Only protium formed in greater abundance. As a result, nearly all available neutrons became locked within helium for nuclei, halting further nuclear progression. This early synthesis was not without constraints. The overall density of matter at the time dictated how much helium-4 could be produced. Had the universe been more compact during Big Bang nucleosynthesis, an even greater fraction of matter would have been funneled into helium, potentially altering the course of cosmic chemistry. In such an alternative scenario, the universe may have contained so much helium, an element chemically inert under normal conditions, that the very foundations of molecular complexity could have been stifled, rendering life as we know it impossible. Astrophysicists estimate that approximately 75% of the universe's baryonic mass after nucleosynthesis was locked in hydrogen, with helium for making up the remaining 25%. This fundamental ratio, exclusive of dark matter, neutrinos, and radiation, directly shaped the formation of the earliest stars, the elusive population 3 stars that astronomers continue to seek. Though hydrogen and helium formed the vast majority of matter, they are but 2 of the 118 elements known today. Where, then, did the remaining elements arise? The answer lies in the ticking clock of cosmic time, as the universe continued to expand and cool. As nucleosynthesis proceeded, the next element in line was lithium, formed through the capture of additional protons. 2 isotopes emerged, lithium-6 and lithium-7, with the latter dominating in abundance. This was followed by beryllium, formed with 4 protons. However, beryllium-7, the only isotope created in significant quantities, was inherently unstable, decaying into lithium-7 within 53 days. An even greater challenge arose with the fleeting existence of beryllium-8. This isotope disintegrated almost instantaneously, within a billionth of a second, preventing it from serving as a stepping stone to heavier elements. In fact, no isotope composed of precisely 8 hadrons is stable, a fundamental roadblock in nucleosynthesis that prevented the formation of elements beyond lithium in any appreciable amount. At this point, the nuclear forge of the Big Bang began to sputter. With fewer heavy nuclei to facilitate further fusion, and with rapidly decreasing temperatures limiting reaction rates, the creation of elements with 9 or more nucleons became vanishingly rare. If any boron, carbon, nitrogen, or oxygen formed at all, it was in quantities so minuscule that no detectable trace remains in the cosmic record. 20 minutes after the Big Bang, the universe's first great act of creation came to an end. The nuclear fires that had spanned the entire observable cosmos cooled into stillness. At this moment, only 4 elements had been forged, and of those, only 3, hydrogen, helium, and lithium, persisted long enough to witness the birth of the first stars. It would take another 200 million years before conditions allowed for a second wave of element formation. As vast clouds of hydrogen and helium collapsed under the relentless pull of gravity, the first stars ignited in brilliant nuclear fusion. Their immense pressure and temperatures, far beyond anything seen in the early universe, would eventually give rise to heavier elements. But the story of those first stars, Their origins, their properties, and their contributions to cosmic evolution remains an open question in modern astrophysics. In our attempt to reconstruct this ancient period of cosmic history, we are left with an unresolved enigma. Observations of the early universe, as inferred through studies of the oldest stars and the cosmic microwave background, suggest a discrepancy between predicted and observed abundances of lithium-7. This inconsistency, known as the cosmological lithium problem, remains one of the most significant outstanding challenges in Big Bang nucleosynthesis. In 2013, astronomers made an impossible measurement. Observations of ancient stars in the Milky Way's halo indicated that their lithium-7 content was significantly lower than theoretical predictions. Despite decades of refinements to nuclear reaction models and observational techniques, this discrepancy persists. Could our understanding of early universe nuclear physics be incomplete? Are there yet unknown processes that deplete lithium in these ancient stellar relics? Or does the answer lie in a deeper, more fundamental revision of the standard model of cosmology itself? The mystery lingers at the very heart of our understanding of the universe's first moments, an unresolved thread in the grand cosmic narrative. And so, as astrophysicists continue their search for population 3 stars and refine their models of nucleosynthesis, they are not merely probing the distant past. They are seeking to answer one of the most fundamental questions of all. How did the universe take shape, and what hidden forces continue to shape it today? The cosmological lithium problem, a scientific enigma at the dawn of time. Among the many celestial bodies that have captured the attention of astronomers, few are as paradoxical as HD 140283, a star that has been observed for over a century. When researchers finally attempted to determine its age with high precision, they were met with an apparent contradiction. This star seemed to be older than the universe itself. Initial calculations placed its age at approximately 14.5 billion years, a staggering result given that the widely accepted age of the universe is 13.8 billion years. Given its antiquity, the star was colloquially named Methuselah, after the biblical figure renowned for his longevity. Naturally, this age paradox pointed not to a flaw in the fundamental chronology of the cosmos, but rather to the limitations and uncertainties inherent in stellar dating techniques. Accounting for systematic errors and refining their models, astronomers subsequently constrained Methuselah's age to approximately 13.66 billion years, comfortably within the universe's timeline. More recent studies published in 2021 suggest it may be even younger, potentially as young as 11.5 billion years. While the exact age remains uncertain, the star's composition provides crucial insights into the early universe. By analyzing Methuselah's chemical makeup, astronomers concluded that it is not a first-generation star, but rather a member of the subsequent population 2 stars, objects that formed after the first stellar generation, known as population 3, had lived and perished. Unlike their predecessors, which contained virtually no elements heavier than helium, population 2 stars like Methuselah exhibit low but non-zero metallicity, approximately 0.1% of the Sun's. Over cosmic time, successive stellar generations enriched the interstellar medium with heavier elements, ultimately giving rise to population 1 stars, such as our Sun, which have metallicities exceeding 1%. The study of population 2 stars is crucial for testing theoretical predictions about the primordial universe. Since the most ancient stars are long gone, their chemical legacy persists as an imprint in stars like Methuselah, allowing astronomers to extrapolate back to the era of Big Bang nucleosynthesis, the period mere minutes after the Big Bang, when the first atomic nuclei formed. However, understanding these relics is not confined to individual stars. Astronomers also examine low-mass dwarf galaxies, which, due to their weak gravitational potential, retain a chemical signature closer to the primordial universe. These galaxies, having experienced relatively little star formation, provide an invaluable laboratory for studying the elemental abundances of the earliest epochs. Observations of ancient stars and low-metallicity galaxies have largely confirmed the theoretical predictions of Big Bang nucleosynthesis for hydrogen, including its isotope deuterium, as well as helium-4. However, when it comes to lithium-7, a glaring discrepancy emerges. The observed abundance is only about 1/3 of what theoretical models predict. This puzzling inconsistency is what scientists have termed the primordial or cosmological lithium problem. The predicted abundance of lithium-7 is derived from a fundamental parameter, the photon-to-baryon ratio at the time of Big Bang nucleosynthesis. This ratio, independently confirmed by observations of the cosmic microwave background, should dictate the production of primordial elements with great precision. Yet, despite the consistency of hydrogen and helium measurements with theoretical expectations, lithium remains anomalously scarce. Scientists have proposed 3 primary explanations for this enduring enigma: stellar processes and observational biases. One possibility is that the lithium is not actually missing, but rather concealed or destroyed in ways we have yet to fully account for. Stars, particularly old and hot population II stars, are highly efficient at depleting lithium through convective mixing and nuclear fusion processes. Given that astronomers can only observe a star's outer layers, it is possible that significant amounts of lithium are hidden beneath the photosphere. Additionally, uncertainties in temperature measurements can introduce systematic errors in abundance estimates, leading to potential miscalculations of the lithium content. Nuclear physics beyond current models. Another avenue of investigation lies in refining the nuclear physics governing lithium's formation. Lithium-7 primarily forms via the decay of beryllium-7. If the nuclear reactions that produce or destroy these isotopes operate slightly differently than current models suggest, it could help resolve the discrepancy. In 2015, a team of researchers reassessed the nuclear pathways of beryllium-7 formation and decay, yet their findings only deepen the inconsistency between theory and observation. New physics and cosmological implications. The most radical solution posits that our understanding of fundamental physics is incomplete. Theoretical predictions for primordial element abundances rely on our knowledge of the 4 fundamental forces: gravity, electromagnetism, and the strong and weak nuclear interactions, as well as the properties of elementary particles and the expansion history of the universe. If the early universe contained unknown exotic particles or interactions that altered nuclear reaction rates, this could provide an explanation. Additionally, the influence of dark matter or unknown variations in the early universe's density distribution might have subtly modified the synthesis of lithium. Another intriguing possibility is that our assumptions about the large-scale homogeneity of the cosmos are flawed. Cosmological models assume that the universe is statistically uniform on large scales, meaning that any observer, no matter their location, should infer the same fundamental properties of the universe. However, if our region of the cosmos is slightly underdense compared to the cosmic average, our local measurements could be biased, leading to discrepancies in inferred element abundances. Resolving the cosmological lithium problem remains one of modern astrophysics' great challenges. Future advancements in observational astronomy, particularly with next-generation telescopes capable of probing the chemical signatures of ever more distant and ancient stars, may help refine our understanding. Likewise, improvements in computational models and nuclear reaction measurements could either confirm or refute current theoretical frameworks. Ultimately, this puzzle is more than a mere technical anomaly. It is a potential window into undiscovered physics, the nature of the early universe, and the evolution of matter from the first instance after the Big Bang to the formation of galaxies, stars, and planets. Whether the solution lies in improved measurements, revisions to nuclear physics, or a profound shift in our understanding of cosmology itself, the answer will bring us one step closer to unraveling the mysteries of the cosmos. And so, we continue our journey, seeking to decode the fundamental narrative of our universe, from its fiery birth to the intricate cosmic structure we inhabit today.
What happens when you think of nothing? Perhaps you picture a vacuum, a region of space emptied of all matter and radiation. But delve deeper. Try to conceive of a true nothing, a state devoid not just of matter and energy but of space and time themselves. Such an absolute nothing is alien to our experience, a concept that resists even our most vivid imagination. Yet, the human mind has grappled with this profound mystery for millennia. The biblical account of creation begins with God bringing the heavens and the earth into existence. But it remains silent on the state of being before creation, a moment outside time, a place beyond space. Similarly, modern science tells us that our universe had a beginning. Around 14 billion years ago, the cosmos emerged in a fiery birth, a hot and dense maelstrom of particles and energy. Since then, it has been expanding and cooling, evolving into the intricate structure we observe today. But the question remains, what came before? Cosmologists offer several tantalizing possibilities. Perhaps our universe is part of an endless cycle of birth, death, and rebirth, or the product of a collision between two pre-existing universes. Yet, one of the most unsettling and intriguing answers is that our universe may have arisen from nothing. If true, this notion challenges our deepest intuitions about existence. How can something emerge from absolute nothingness? What mechanisms could make such a leap possible? To approach these questions, we must examine the very fabric of reality. Consider the vacuum, a seemingly empty region of space where electric and magnetic fields are at zero. Is such a vacuum truly empty, or does it possess hidden potential? By the early 20th century, experiments and theories began to reveal a more complex picture of emptiness, fundamentally altering our understanding of physical reality. The deterministic, clockwork universe envisioned by Newton had already been upended by Einstein's theories of relativity, which redefined space and time as dynamic and interconnected. Meanwhile, the realm of the very small, the world of atoms and subatomic particles, was proving even stranger. Here, certainty gave way to probability, governed by the groundbreaking mathematics of quantum mechanics. Quantum mechanics describes a world where particles do not have definite positions or velocities until measured. Instead, they exist in a haze of probabilities, their behavior dictated by wave-like functions. In this realm, empty space is not truly empty. Quantum fluctuations, temporary changes in energy, occur spontaneously, giving rise to particles and antiparticles that briefly appear and annihilate each other. This phenomenon suggests that the vacuum is teeming with activity, a seething cauldron of potential rather than a void. This quantum strangeness has profound implications. It means that the universe as we know it may have originated from such fluctuations. During the earliest moments of the Big Bang, the nascent cosmos was governed by quantum laws, and its very existence may have been a quantum event. If quantum fluctuations can spawn particles and energy, they might also give rise to entire universes under the right conditions. But this leads us to a deeper question: why do the quantum laws themselves exist? Why does the framework that allows for something to emerge from nothing exist at all? These questions touch on the fundamental nature of reality and point to the limitations of current scientific understanding. The quantum world, with its probabilities and uncertainties, underpins everything we observe on macroscopic scales. Its effects are subtle yet ubiquitous, shaping the evolution of stars, the behavior of materials, and even the structure of spacetime. To explore the full impact of quantum mechanics on the universe, we must embark on a journey across time and space. From the earliest moments after the Big Bang to the eventual fate of the cosmos, quantum phenomena play a central role. They provide insights into the formation of galaxies, the nature of black holes, and the mysterious dark energy driving cosmic acceleration. These phenomena also challenge our perception of reality, suggesting that the macroscopic certainties we experience are merely approximations of a fundamentally probabilistic world. By probing the quantum underpinnings of the universe, we inch closer to addressing the ultimate question: where did everything come from? While science has yet to provide a definitive answer, the interplay between quantum mechanics and cosmology offers a tantalizing glimpse of the profound mysteries that lie at the heart of existence. Perhaps, in understanding the quantum nature of nothingness, we will uncover the secret of how something can emerge from nothing, reshaping our view of reality and our place within it. The world of probabilities. In the early 20th century, the world of physics was undergoing a transformation. Traditional ideas, rooted in Newtonian mechanics, struggled to explain the behavior of the very small. Electrons, for instance, were thought to orbit the nucleus of an atom much like planets orbit the sun. But calculations showed that such an atom would collapse almost instantly. What, then, kept electrons in motion without destroying the atom? By 1900, Max Planck had already introduced a revolutionary concept: energy was quantized, existing in discrete packets rather than a continuous flow. This idea emerged from his study of blackbody radiation and marked the birth of quantum mechanics. Over the next 2 decades, the theory expanded to include the quantized orbits of electrons around nuclei. Yet the details of these orbits eluded physicists, and their attempts to explain the motion of electrons faltered under the weight of unruly mathematics. Werner Heisenberg, a young physicist, was among those grappling with these challenges. Exhausted from months of failed calculations and hampered by hay fever, he retreated to the remote island of Heligoland in the North Sea, seeking clarity in its fresh, salty air. It was there, one evening in 1925, that inspiration struck. He realized that the key to understanding electrons lay not in their precise motion but in what could be observed: the frequencies of light emitted when electrons transitioned between energy levels. Heisenberg abandoned the idea of tracking electrons in their orbits. Instead, he focused on the measurable properties of these transitions. This shift in perspective led him to develop a new mathematical framework using matrices. At the time, matrices were an unfamiliar tool in physics, but they proved remarkably effective in describing the behavior of electrons. By discarding the unobservable and focusing solely on the observable, Heisenberg had uncovered a new way of thinking about the quantum world. This breakthrough revealed a reality far stranger than anyone had anticipated. Electrons, as described by quantum mechanics, did not exist in fixed positions or follow definite paths. Instead, they were represented by a wave function, a mathematical entity that encapsulated the probabilities of finding an electron in a particular location. When combined with Erwin Schrödinger's wave equation, Heisenberg's work painted a picture of a universe where certainty was replaced by likelihood. One of Heisenberg's most profound insights was the relationship between an electron's position and its momentum, a measure of its speed and direction. He discovered that the more precisely one of these properties was known, the less precisely the other could be determined. This principle, now known as the Heisenberg uncertainty principle, is a cornerstone of quantum mechanics. It reveals a fundamental limit to what can be known about the quantum world, a consequence not of experimental shortcomings but of the very nature of reality. To illustrate this, imagine placing an electron inside a tiny box. In classical physics, cooling the electron would slow it down until it eventually came to rest at absolute zero. But quantum mechanics forbids this. The act of confining the electron creates uncertainty in its momentum, ensuring that it always retains some residual motion. This perpetual jiggling, inherent to quantum systems, reflects the interplay between position and momentum as dictated by the uncertainty principle. The implications of this principle extend beyond particles in boxes. Energy and time, like position and momentum, are also subject to quantum uncertainty. As a result, energy can fluctuate over very short timescales, allowing particles to appear and disappear briefly. These fleeting occurrences, known as quantum fluctuations, imbue empty space with a residual energy known as the quantum vacuum. Far from being truly empty, this vacuum teems with virtual particles that flicker in and out of existence, a manifestation of the uncertainty principle on a cosmic scale. This quantum reality, so disconnected from our macroscopic experience, underpins much of the universe's behavior. For instance, it prevents electrons from spiraling into nuclei, stabilizing atoms, and enabling the existence of matter. It also influences phenomena on a grander scale, such as the evolution of stars and the structure of spacetime. In the quantum world, the impossible becomes commonplace, and even nothingness is something. The quantum of cosmos present. What truly powers the stars that light our skies and warm our world? For much of human history, the sun was shrouded in mystery and awe. To the Egyptians, it was Ra, the king of gods. To the Greeks, it was Helios, guiding his chariot across the heavens. But beyond mythology lay deeper questions. Was the sun merely a great ball of fire? And if so, what sustained its burning brilliance for eons? These questions sparked some of the most profound discoveries in science, leading us to the strange and wondrous world of quantum mechanics, a realm that underpins the very fabric of the universe. In the mid-1800s, Lord Kelvin, a pioneer in thermodynamics and namesake of the Kelvin temperature scale, sought to calculate the sun's age. Based on the physics of his time, he proposed that the sun's immense heat was due to gravitational compression, an immense ball of gas squeezed to high temperatures by its own weight. This explanation, however, imposed a troubling limit. The sun could only sustain its light and heat for a few million years. This estimate contradicted the geological and biological evidence of Earth's history, which demanded far greater timescales. Yet, Kelvin's calculations lacked a crucial element, the physics of the atomic nucleus. By the early 20th century, scientists had unraveled the structure of the atom, revealing that its nucleus contained positively charged protons and neutral neutrons bound together by the strong nuclear force. This force, unimaginatively named but profoundly powerful, is what holds the nucleus together despite the intense repulsion between its positively charged protons. With the discovery of nuclear reactions, physicists realized that the strong force could unleash vast amounts of energy. It was Cambridge astronomer Arthur Eddington who first suggested in 1920 that the sun's power lay in the fusion of atomic nuclei, a process that transforms lighter elements, like hydrogen, into heavier ones, such as helium, while releasing energy in the process. Fusion, however, posed its own challenges. For nuclei to fuse, they must overcome the electromagnetic repulsion between their positively charged protons. The strong force acts only over incredibly short distances, meaning the nuclei must be brought into almost direct contact for fusion to occur. Even in the sun's core, with its crushing gravity and temperatures nearing 15 million Kelvin, classical physics suggested that collisions between protons were too gentle to overcome this barrier. How, then, could the sun shine? The answer emerged from the quantum realm. In the 1920s, physicist George Gamow proposed a solution rooted in quantum mechanics. At the quantum level, particles do not behave like solid billiard balls. Instead, their positions and energies are described by probabilities. This uncertainty allows for a phenomenon known as quantum tunneling, where particles can borrow energy to overcome barriers they would not surmount in a classical system. In the sun, this means that protons can tunnel through the electromagnetic repulsion barrier, enabling fusion to occur despite the apparent improbability. This insight revolutionized our understanding of stellar energy and cemented quantum mechanics as a cornerstone of astrophysics. Through the mid-20th century, scientists pieced together the intricate nuclear reactions that fuel stars. Hydrogen nuclei fuse to form helium, releasing energy and driving the sun's radiance. In more massive stars, fusion proceeds to heavier elements, creating carbon, oxygen, and up to iron in their cores. But these processes have a limit. Fusion beyond iron consumes more energy than it produces. The creation of elements heavier than iron requires the extreme conditions of a supernova, the explosive death of a massive star. Here, the interplay of quantum physics and astrophysics takes center stage. Neutrinos, ghostly particles first posited by Wolfgang Pauli in the 1930s, play a pivotal role in supernovae. These particles interact only through the weak nuclear force, making them extraordinarily elusive. Trillions of neutrinos pass through your body every second without leaving a trace. Despite their near invisibility, neutrinos are critical in the collapse and subsequent explosion of massive stars. During a supernova, the core of a dying star collapses under gravity, forcing electrons into protons and producing a flood of neutrinos. These neutrinos interact with the outer layers of the star, reversing the collapse and triggering a cataclysmic explosion that spews newly formed elements into the cosmos. Quantum mechanics is not merely a curiosity confined to the microscopic world. It is woven into the fabric of the universe, shaping the stars and seeding the cosmos with the elements essential for life. Yet, its influence may extend even further. Could quantum physics explain the very origins of the universe? Is the cosmos itself a quantum object? In quantum mechanics, a wave function encapsulates all the information about a particle or system, describing its probable states. For two particles, we use a single wave function to describe their combined state. Extending this idea, physicists have speculated that a single wave function might describe the entire universe, encompassing every particle, every photon, and every quantum fluctuation. This wave function of the universe would be an immense but theoretically conceivable construct, offering a probabilistic map of all that exists. This perspective challenges the deterministic worldview of classical physics, where knowing the precise state of every particle at a given moment would allow us to predict the future with certainty. In quantum mechanics, however, the future is not fixed but unfolds as a series of probabilities. Hugh Everett III, in the 1950s, proposed the radical many-worlds interpretation, suggesting that every quantum event spawns a multitude of parallel universes. In this multiverse, every possible outcome of a quantum interaction is realized, creating an infinite tapestry of alternate realities. While this idea remains controversial, it underscores the profound implications of quantum theory for our understanding of existence. Even the origin of time itself may be rooted in quantum physics. In the early 1980s, Stephen Hawking and James Hartle proposed a model in which the quantum nature of spacetime rendered the concept of a singularity, a point of infinite density and zero volume, irrelevant. In their no boundary proposal, time behaves like a spatial dimension in the earliest moments of the universe, gradually transitioning into the familiar temporal flow as the cosmos expands and cools. This idea suggests that the universe had no distinct beginning in the classical sense, but emerged smoothly from a quantum state. To explore these questions further, we must venture back to the first trillionth of a second after the Big Bang, where the quantum and cosmic converge. In this epoch, known as the Planck era, the energies and densities were so extreme that the classical laws of physics break down. Quantum fluctuations during this time may have seeded the structures we observe in the universe today, from galaxies to clusters of stars. Understanding this epoch requires uniting quantum mechanics with general relativity, a goal that remains one of the greatest challenges in physics. The interplay of quantum mechanics and cosmology offers a glimpse into the profound interconnectedness of all things. From the sun's warmth to the elements that compose our bodies, from the life cycles of stars to the origins of the universe itself, quantum physics provides a framework for understanding the cosmos at its most fundamental level. It invites us to rethink reality, embracing the probabilities and paradoxes that define our existence and seeking answers to the deepest questions of all: where did we come from? Why are we here? And what lies beyond? The quantum of cosmos past. In the 1970s, Alan Guth, a physicist turned cosmologist, faced a conundrum involving magnetic monopoles. Unlike the magnets we are familiar with, which always have both a north and a south pole, monopoles would exist as purely north or purely south, a peculiarity predicted by certain early universe theories. If the universe had once been governed by a single superforce, a primordial unification of the four fundamental forces, magnetic monopoles should have emerged in abundance during the universe's infancy. However, despite their theoretical significance, no monopoles had been observed. Where were they? Guth realized the solution lay in rethinking the dynamics of the early universe. In 1981, he proposed a groundbreaking theory: inflation. He suggested that the universe, shortly after its birth, underwent an extraordinarily rapid expansion. During this inflationary epoch, spacetime itself stretched exponentially, diluting the density of magnetic monopoles to the point of near invisibility. In the vastness of the observable universe, perhaps only a single monopole might remain, forever eluding detection. But Goose's theory offered more than just a hiding place for monopoles. It explained why the universe appears so smooth on large scales. When we observe the cosmos, we see a remarkable uniformity. Galaxies are evenly distributed, and the temperature of the cosmic microwave background, CMB, the faint afterglow of the Big Bang, is astonishingly consistent. Why should this be the case? In Goose's model, the observable universe grew from a minuscule, smooth patch of spacetime that inflation magnified to cosmic proportions. This initial uniformity became the smoothness we observe today. Yet inflation also provided the seeds of cosmic structure. The quantum world, with its ceaseless fluctuations, played a crucial role. Even in the smoothness of an inflationary vacuum, Heisenberg's uncertainty principle ensured that tiny energy variations occurred. These quantum fluctuations, frozen into spacetime by inflation, became density variations as the universe cooled. Over billions of years, gravity amplified these slight overdensities, drawing matter together into the galaxies, stars, and planets that populate the cosmos today. The evidence for this process is written into the CMB, the oldest light in the universe. This ancient radiation carries an imprint of the quantum fluctuations that seeded the large-scale structure of the cosmos. Observations of the CMB by missions like COBE, WMAP, and Planck have revealed subtle variations in temperature, echoes of those primordial quantum ripples. In this sense, the quantum world has shaped not only the microscopic but also the macroscopic, bridging the infinitesimal and the infinite. But could the quantum go even deeper, answering the ultimate question of where the universe itself came from? In 1973, physicist Edward Tryon offered a provocative suggestion: maybe the universe is a vacuum fluctuation. His idea was rooted in the peculiar properties of the quantum vacuum. In quantum mechanics, even empty space is far from empty. Instead, it teems with fleeting fluctuations, where particles and antiparticles briefly pop into existence before annihilating each other. Tryon speculated that the universe might be the result of such a fluctuation, a spontaneous emergence of spacetime itself. How could this be? Tryon considered the universe's total energy. While the mass and motion of matter contribute positive energy, gravitational fields contribute negative energy. Remarkably, these two quantities might exactly cancel, leaving the total energy of the universe at zero. In this scenario, the universe could arise from a fluctuation without violating the conservation of energy. If its total energy is zero, the universe could, in principle, exist indefinitely, a quantum fluctuation writ large. Of course, this hypothesis raises further questions. If the universe is a fluctuation, where did the quantum fields that enabled it come from? What existed before spacetime? These are questions that push beyond the limits of current scientific understanding. While quantum mechanics allows us to conceive of something emerging from nothing, the nature of true nothingness, a state devoid of space, time, and quantum fields, remains a mystery. Despite these uncertainties, it is clear that quantum mechanics played an essential role in the universe's earliest moments. Within the first trillionth of a second after the Big Bang, quantum processes governed the dynamics of inflation and set the stage for the cosmos we inhabit. Yet, as we ponder the universe's origins, we are also drawn to its distant future. Could the quantum continue to shape the fate of the cosmos? The quantum of cosmos future. What does the future hold for the cosmos? As we peer into the distant eons to come, we find ourselves contemplating a universe gradually growing darker and colder. Could the laws of quantum mechanics, which shaped the birth of the universe, also determine its ultimate fate? In its youth, the universe was a prolific creator of stars. The majority of all stars that will ever exist were born within the first few billion years of cosmic history. Over the subsequent 9 billion years, star formation has slowed significantly, and the ability of the universe to give rise to new stars is rapidly diminishing. In the distant future, only a faint trickle of stars, the final 5%, will emerge. But stars, like all things, are mortal. Massive stars live fast and die young, their lives lasting mere millions of years before spectacularly ending in supernovae. Stars like our Sun endure for billions of years, but even they eventually exhaust their nuclear fuel. Only the tiniest and dimmest stars, red dwarfs, can sustain themselves for tens of trillions of years, burning their fuel with exquisite efficiency. Yet, even these diminutive stars will eventually flicker out, leaving behind dark, inert husks scattered throughout an ever-expanding cosmos. What happens when a star dies? Without the outward pressure from nuclear fusion to counteract gravity, one might expect the star to collapse entirely, crushed out of existence by its own weight. However, a surprising and subtle force steps in to halt this fate, the quantum degeneracy pressure of electrons. As a star cools and contracts, gravity compresses its material into an increasingly smaller volume. The electrons within the star are forced into close proximity, confining their possible locations. According to Heisenberg's uncertainty principle, restricting the electrons' positions increases the uncertainty in their momenta, imparting a residual motion that persists even at absolute zero. This quantum jitter creates a degeneracy pressure, which counterbalances gravity and prevents further collapse. The result is a stable remnant, such as a white dwarf, that can persist in the darkness for trillions of years. Yet, even these remnants are not eternal. On cosmic timescales stretching beyond human comprehension, the stability of matter itself comes into question. While protons are often considered stable, some theories suggest they may decay under the influence of yet undetected forces. If true, proton decay would spell the dissolution of matter on timescales of years. Dead stars, stripped of their structural integrity, would dissolve into a sea of elementary particles, leaving behind a universe devoid of complex matter. In this bleak expanse, only black holes would remain, the final guardians of the cosmos. Black holes, regions of spacetime so warped by gravity that nothing can escape, might seem impervious to decay. Yet, as Stephen Hawking famously demonstrated, even these titanic entities are not immune to the laws of quantum mechanics. The culprit is the quantum vacuum. Far from being empty, the vacuum seethes with fluctuations, where pairs of virtual particles and antiparticles briefly pop into existence before annihilating each other. Near the event horizon of a black hole, this balance is disrupted. The intense gravitational gradient separates the particle pairs, allowing one particle to escape while its partner is consumed by the black hole. This process, known as Hawking radiation, draws energy from the black hole itself, causing it to gradually evaporate. Over unfathomably long timescales, black holes will lose mass and energy through Hawking radiation, shrinking until they finally vanish in a faint burst of energy. With their disappearance, the universe would reach its ultimate asymptotic state, a dark, cold expanse where even the faintest traces of structure have dissolved. And yet, the question remains, is this truly the end of the story? Could the quantum nature of the cosmos, which once birthed stars and galaxies, also hint at new beginnings? As we gaze into the depths of time, we find ourselves at the limits of both imagination and science. The quantum of the cosmos has guided the universe through its grand arc of creation, transformation, and dissolution. Perhaps it holds secrets yet to be discovered, whispering of futures we can scarcely conceive. Looking through the singularity. In 1958, whispers of such a theory electrified the physics community. Giants of quantum physics, Werner Heisenberg and Wolfgang Pauli, had reportedly developed a framework uniting quantum mechanics with Einstein's general relativity. It was a tantalizing prospect, two towering figures from the quantum revolution revisiting the stage with a solution to a problem that had stymied generations. Pauli presented their ideas at Columbia University, with physicists traveling from Princeton to witness what they hoped would be a historic unveiling. But as Pauli spoke, it became clear that their theory could not hold. The idea that all particles were manifestations of a single fundamental entity failed to match experimental evidence. Freeman Dyson, in attendance, likened the event to watching the death of a noble animal. Despite their brilliance, Heisenberg and Pauli's attempt joined the long lineage of failed theories, a graveyard of disappointed hopes that even Einstein himself lamented. Einstein had pursued a unification of forces for decades. The addition of electromagnetism to his general theory of relativity by Theodore Kaluza sparked excitement, but the equations resisted the inclusion of quantum mechanics. Einstein's subsequent efforts remained incomplete at his death in 1955, epitomizing the struggle to reconcile gravity's smooth curves with the quantum world's discrete probabilities. Today, this search for a theory of everything continues, paradoxically hindered by the extraordinary success of its components. General relativity is a flawless description of gravity on large scales, underpinning technologies like GPS quantum field theory. The modern framework for quantum physics has revolutionized our understanding of the strong, weak, and electromagnetic forces. It describes particles as ripples in underlying fields, electrons in the electron field, photons in the electromagnetic field, with astonishing precision, confirmed by experiments like those at the Large Hadron Collider. Yet, the mathematics of these two theories is fundamentally incompatible. Where relativity describes spacetime as a smooth continuum, quantum mechanics demands discrete, probabilistic interactions. Attempts to merge the two result in equations plagued by infinities, nonsensical outputs that signal the need for a deeper understanding. Theoretical physicists, deprived of experimental guidance, have ventured into a landscape of possibilities. String theory suggests that the fundamental constituents of the universe are tiny vibrating strings, their modes of vibration determining the properties of particles. Loop quantum gravity envisions spacetime itself as a woven network of discrete loops. Other proposals explore extra dimensions, hypothesizing that our universe is a three-dimensional brain floating in an 11-dimensional bulk. Whether any of these theories holds the key remains unknown. But let us imagine that the puzzle is solved, that a theory of everything emerges. What secrets might it unveil? The first target would be black holes. In general relativity, the mass of a black hole is compressed into a singularity, a point of infinite density where the known laws of physics break down. Infinities have no place in physical theories, and a theory of everything could eliminate the singularity, revealing the true nature of a black hole's core. The same applies to the singularity at the beginning of the universe. The Big Bang model describes a cosmos that begins from an infinitely dense state, but this infinity halts our understanding, preventing us from probing what came before. A theory of everything might resolve this, unlocking the ability to peer beyond the Big Bang. What might we find? One possibility is that our universe is a cyclical entity, born from the remnants of a previous cosmos. Another tantalizing idea is the multiverse, where our universe is just one among countless others, each with its own unique laws of physics. Alternatively, we might confront a more unsettling conclusion, that our universe is a random fluctuation, a transient bubble of order in a backdrop of chaos, its existence fleeting and purposeless. This pursuit of the ultimate theory is not just about equations and experiments, it is about confronting the profound questions of existence. Where do we come from? Why does the universe exist? And what is our place within it? While we cannot yet answer these questions, the journey toward a theory of everything continues, fueled by curiosity and the hope of revealing the cosmos in its most fundamental form.